Cool. Hello, everyone. I'm Thomas from Weights and Biases, and here we are with the Autogen team. And we are the Hacker Cup series of talks. So we get you started on this competition where we're trying to solve a very hard um, coding problems with AI. So I will handle to Wei Wei now, so she can introduce the team. And we have Andy, we have Amber, and Wei Wei.
Hi everyone, thank you for joining in. And today I'm super excited to have the team from Microsoft Research who actually created the Autogen portion of the starter kit for this competition. And Andy here, he actually works with these like agent, and Amber, who is a senior software developer, working closely with AI human interactions. And I'm really excited to hear about Andy's research, and Amber can tell us a bit about her experience using Autogen to solve these really hard questions. So Andy, maybe you can kick us off?
Absolutely. Let me just share my screen. And I can kick it off. It actually shares it. Okay, perfect. Cool. So today I'll talk for a little bit, and then I'll hand it over to Amber, who's my teammate, and we also have David with us, who is in the chat, hopefully going to answer some questions for you live. So this is going to be sort of a two-part talk. The first part, I'm going to sort of talk about, how, why, and exactly whether these multi-agent frameworks work. And then I'll talk a little bit about my personal kind of experience with them before moving on and giving it to Amber to actually get into how this can be applied to these challenges in this competition. So the team is Amber, who's the actual person who started writing this code with me, and David, who joined us on this effort. And I'm just the kind of high-level person who just throws some ideas and sees whether they stick or not. And without further kind of dithering, here's kind of overview of what even multi-agent frameworks are about. So as I mentioned, I'm going to talk about some kind of basic, philosophical kind of questions of what these things are, why we are even talking about them, how do they work, do they actually work? And maybe we're going to get to some kind of answers here during the time that we have. So to get to what multi-agent frameworks are, first we have to define what an agent is. And for me, an agent is basically ChatGPT is a good example of an agent. It's a chatbot that has some tools. And typical interactions that you have with a single agent is sort of a back and forth chat with an AI model that maybe has some tools that it's equipped with, doing external API calls, having a Python interpreter available to it, and so on. But it's really just a back and forth interaction between you and this agent. By comparison, a multi-agent framework is, you take a few of these agents that are, again, defined by an AI model and some kind of tools that are given to it. And perhaps these agents, are all kind of uniform, or maybe there is different kind of agents with different set of tools, maybe different models. They have different meta prompts. And the interaction that you have with this framework is you chat with some kind of representative of this framework. They chat between themselves. They come up with some kind of answers, and then they come back to you, hopefully. And the idea here is that, this is something that potentially is going to lead to better results. At least that's what we're hoping for, in the context of this competition. And then I'll tell you maybe a little bit about, some practicalities here. But this is basically the idea. I mentioned there's multiple agents, but how do you define, how do you decide how many agents and what kind of agents? That sort of depends on the task that you have. in a way, you can think about it that the task that you're given, it might heavily inform the kind of orchestrations of these multi-agent systems that you might want to use. In some cases, you just might have 2 agents, maybe more. There's going to be some sort of group chat between them. Often, what turns out to be useful is to have some sort of commander or manager that directs other agents. Sometimes it's a democracy where everyone kind of talks to each other. And this really depends on the specific applications. There is really nothing principled here apart from some inspirations from how organizational structures work. And the actual motivation for these things sort of arose back in the 80s when Marvin Minsky, who was kind of like one of the founders of AI, for those of you who kind of are new to the field, and he had this ideas where he tried to kind of figure out how higher level processing, the kind of reasoning and so on, happens in human brains. And he posited that the kind of cognitive abilities that we care about, like logical reasoning and language abilities and so on, arise as a sort of efficient collaboration between multiple specialized entities, or agents, as he called them. And the idea in this really cute book of his that I highly recommend that you read is that you can combine these agents into these societies, and in principle, these simple agents, when organized in a proper way, can be capable of a lot more than a single agent. And motivations can come from observing the biological world with ants and bees, human societies. In general, it seems to be the case that organizing some smaller agents into a bigger system can give you a lot of benefits. And often, so this kind of sort of makes you start thinking about sort of organizational structures where you can look at maybe these multi-agent collaborations as actual like semi-independent entities, and they're working in some kind of big organization like a tech company or something like this. But with you're given a specific goal to this collaboration, and hopefully the interaction between all of these agents gives you something that actually works well. So let's keep this kind of organizational picture in mind. And I'll talk briefly about why this can have some benefits in a sort of broad way, and then we'll kind of jump into the technicals of it. But roughly speaking, there's probably many more benefits than this, but I'll just focus on 3, which are the modularity of the thing, specialization, and collaboration. And pretty obviously, if you work with AI models, you immediately run into this thing that they're kind of black boxes. There's been a lot of work done on trying to understand what happens inside of the black box of a neural network. But at the end of the day, we're just getting some kind of rough measurements from it. And the thing that we know we have the best control is inputs and outputs. So in a way, if you have this kind of multi-agent framework, these are effectively chatbots. So you have inputs into them, you have their meta prompts, and then you have their answers for the given prompt. And if you have multiple agents, then you end up with a system where you at least have a lot of messages being passed that are completely interpretable. So in this case, this gives you a few things. One is obviously, if we're trying to perform some kind of complex tasks, you have small specific modules, and you can kind of test them each independently. In a way, this also allows you to be somewhat modular in your design and being capable, you can start with a very simple system and then just add capabilities in a sort of more controlled, principled way, but just adding new agents that are going to be that are going to give you these new capabilities. So imagine that you start with a system that can write code, and maybe it goes from text to code completions. But then if you wanted to add another capability to the system so that it doesn't only just take in text, but it also maybe reads in some data from some kind of database. This database might have some images as well to it attached. This is something that you could grab this original system and then completely rewrite, or you could just add another agent, that deals with vision processing, and another agent that has calls to this database. And then suddenly you have a system that, again, you've added a couple of capabilities here that massively expand its potential, but you've done it in a way where you didn't break the piece that you knew that worked. So in general, this is sort of like a nice framework to just play and experiment with. The specialization here is is useful in the sense that this is sort of obvious from the outside of the multi-agent framework. You instead of dealing with know-it-all, master of all, single AI model, which probably doesn't exist, you can now deal with very specialized AI models with their own set of meta prompts and maybe one or two tools that you can kind of more depend on. And this is something that you probably have experienced if you've used, large language models. It's much better to force them into one specific task if you want to have structured outputs and structured data processing throughout the process. This is something that comes up if you're trying to solve for example, the kind of problems that we have in this competition, but maybe also other sort of problems. If you're dealing with structured data and you're trying to do reasoning, then you find yourself often in a situation where you want to preserve structure in the steps of reasoning that you're doing. And to get to that, you really want to have very concrete examples that you present for in-context learning to your AI model. And this is much easier to be done if your task is really broad and there's many steps to it. It's really easier to chunk it. And this sort of arises, this sort of comes from the fact that a lot of problems that we're given, often they're modular in their form. And what this means is, if you're given a problem, you can often break it up into subtasks pretty cleanly. And if that is possible, then this kind of multi-agent framework is going to be highly efficient. You can sort of think about it, in basic CS, we have these concepts of dynamic programming and things like this, where you can, effectively chunk a problem. This is sort of a similar situation in which, if there is kind of hierarchical nature to the overall task, then having submodules is useful. And the last bit is sort of this collaboration aspect. And here's a few reasons for why collaboration of AI models could, in principle, give us something. One is that if you have multiple agents, even just two, they can critique each other's work. Now, this is naively maybe not that useful, but think about this interaction that you have often with a chatbot. My personal experiences, if I use ChatGPT, is that I ask for some kind of, help with maybe coding up some kind of specific task. And then it comes up with some kind of answer that is kind of there, but not exactly. There's some kind of problems with it. So I have to, go in and suggest, hey, actually, you didn't do exactly what I wanted. You missed something, or, actually, I meant to do something in this other framework. And if you now have two agents that chat with each other, they can play this role, and they can at least do some of the feedback between each other without the user having to take so much, effort to get to a final answer. Separately, if you have now multiple agents, you can kind of imagine this as a sort of brainstorming situation in which these agents have very different insights, but potentially they have, very different goals, and they have different meta prompts that lead them to think about the problem from very different directions. One of them could be just prompted to be kind of a creative director and just spew ideas with very high temperature settings, allow it to hallucinate a lot, and then use this kind of hallucinations to your advantage to come up with some kind of creative solutions for other agents that are maybe a lot more technical and run with in a very deterministic fashion. So you kind of started seeing that you could potentially combine agents, at different temperatures, with different meta prompts, and that maybe is something that goes around, goes beyond this capability that you would have from a single agent, because again, a single agent is going to be limited to generations that are specific to the conditions that you used in prompting it. That means it is highly dependent on the system meta prompt that you give to it, the prompts that you feed into it, and or we'll go into some of the other stuff that is related to that, but also just the simple hyperparameters that you use for running a large language model. They lead to very different answers, and even playing with that within a multi-agent framework can give you some benefits.
Can I ask you a question about this?
Absolutely.
Yeah, I'm curious, when you say meta parameters, or this is different version of the same agent, or you call them different agents? If I call the same model with just temperature 0.7 and 1, that would be two different agents?
It could be two different agents if I have them explicitly, independent from each other. Okay. Here's an idea for, and then I'll actually get to this in a second. So this was a great question. My multi-agent framework could be just two models, two instances of the same large language model, and I just run one at high temperature, one at low temperature, and then maybe both are given slightly different meta prompts. But there's other hyperparameters that I could play with. If you go into, for example, ChatGPT is a popular one, but if you go into the API version of this, you have the temperature as a slider, you have the top P sliders, you can give different stopping conditions and so on. All of these could be just a slightly different way that you use a given model. And if you freeze that now as your set of parameters, I would call that an independent agent.
Okay.
And this is actually a perfect segue into my next point, which is this. We started with this multi-agent kind of organization thing, but here's the critical point. Often, it's all the same model all the way through the whole architecture. So this gets me to this point, which is how is it possible that it's all ChatGPT talking to ChatGPT and so on? How can this actually give us any improvements over just a single base model? Because if we're just doing routing information from the same model into the same model into the same model, it becomes a little bit more kind of crazy to think that you would get any advantages from sort of a uniform society, because you kind of have this imagination that when you prompt a model, you extract some kind of capabilities from it, but all of these capabilities are hidden inside of it. So in a way, you would think, hey, if I'm creating this multi-agent architecture out of a single model, maybe I could come up with a very clever meta prompt and just skip this whole multi-agent setting. If I had a very carefully designed meta prompt, then maybe I could do some sort of chain of thought kind of reasoning in a system that would emulate exactly the same stuff that happens on a multi-agent framework, and you can just skip that completely. And first of all, this could be this, and I just want to say, for simple problems, this might be the case that you don't need multi-agent frameworks. If this would be indeed the case, then you would save a ton of money, because you would be just calling one model, not many models that are doing some kind of feedback loops with each other. But it just so happens that even with a single model, you can set things differently enough that this actually still makes sense. And I'll talk about 3 reasons for this. One of these is dependent on some models, but many of the popular open source LLMs are mixtures of experts. And I have no ideas whether any of the big, popular models are, because none of their architectures are known. But if a model is a mixture of experts, then what this means is that as you're training this network, you had separate layers that are kind of parallel to each other within the network. And often when you're running some kind of completions of a prompt, what happens is that this information gets routed through one or just a few experts throughout the whole network. So typically when I try to complete things and I ask my model to write code, it often will just go through one of the experts that just happened to kind of self-organize through training to be an expert on coding. So what you end up getting is that a single pass, again, goes through just a subset of, a single completion goes through only a subset of experts, or maybe just one expert. And if now I would be using multiple agents and split up the initial task into sub-problems, I might be able to query different parts of the model and hence different parts of its expertise. So this is immediately starting to kind of look like, hey, I can actually try to explore more broadly the capabilities of this model by using different agents rather than just using one agent. A second reason is if we are doing some sort of reasoning, which is going to be crucial to this competition, if you look at what we understand about our capabilities to do logical reasoning and kind of math capabilities and abilities to reason about code and reason about programming challenges, this heavily seems to depend in our brain on sort of slow kind of iterative reasoning that happens in our heads. Some people call this system 2, in which you start with some kind of maybe hypothesis, then you evaluate whether this makes sense, you make some kind of corrections to your improvement, and you go through this deduction induction kind of stages. This is sort of like you test your hypothesis, doesn't exactly work, you correct it, you improve things until you find a solution. Like if you've ever sat down and tried to prove a mathematical theorem or something like this, you will see that you go through this kind of stages until you make the right kind of guess and then verify that this is indeed the case. So first of all, this kind of iterative thing seems to be the way that we think. And if you kind of test this out, running large models in sort of iterative loops actually gives you a lot of performance boosts, at least in doing some kind of logical reasoning challenges. So at least you would want some kind of non-trivial framework in which the model makes calls to itself or makes calls to something else that makes calls to itself, etc. And the other reason is if you look at just purely neural networks, then recursive calls are something that expands your overall space of the things that you can approximate, and you need recursion to have Turing universal, Turing universal computation. So this tells you that there is some overall bigger power in being able to do recursion and iteration in a network. So at least you want something along those lines. And the last bit here is we're all kind of familiar with it. Anyone who has used large models knows that it's really, really finicky. And large models are super sensitive to small changes in the initial prompt. Here's a few examples of it that are very popular. You're given a problem, and you can prompt it in a few different ways. You can give it several examples beforehand of the kind of answers that you will want to get from it. You can force it to do so-called chain of thought prompting, in which you force the model to kind of write out its answer by reasoning first about the relevant steps. This is sort of to fake this iterative reasoning, if you wish. Um, but you can do this in multiple ways. And sometimes you get the same answer, sometimes you get different answers. And often you get better answers the more explicit the thinking is forced in the prompt itself. But even outside of this, if you just flip some words in a prompt, you often get very different answers. Even if the meaning of the sentence is the same, the model just does completion based on the initial distribution of words, and it's a probabilistic model, so it's going to give you different answers. So overall, we know that these things are super sensitive, and this means that if we're going to be trying to if we're going to grab multiple agents and we'll try to extract all of the meta prompts and combine them into one, that combination process itself is going to be super sensitive. So this means that it's really going to be difficult to obtain this, all models into one. And with that, I'm going to jump into a short case study of, do these multi-agents actually work? And this is going to be from my own research. Yeah.
Andy, before you move on, we have a question from chat. Do you get better results if you mix the various models? So, for example, Claude, Llama, ChatGPT into multi-agent settings, or you get better results with just the same model?
That's an excellent question, and I think it's really dependent on the specific, situations. I have personally seen that sometimes combining different models can lead to better performance, but it really is highly specific to the task, to the models that you're using, and it's sort of a Wild West out here right now. We don't have an answer to this question. We know that combining things seems to do better. Exactly how you're supposed to do this is sort of still up in the air, and it's up to you to experiment with it.
Yeah, I can add that some of the customers we have also are vendor locked. So knowing that you can prompt the same model differently gives you like some idea of how to create these agents, even if you don't have access to all the models available.
Exactly. I mean, yeah, I'm in a similar situation where I use, multiple models, but it's often easier just to use one API. Yeah. And it goes both ways. I've tried using multiple models, and you can get some really interesting things. Often even combining a weaker model into it gives you it injects some kind of chaos into the whole thing that could be beneficial. So let me run quickly through a nice little example of this that is completely unrelated to what is in this challenge. But my personal work has been on applying large models to instead of game engines, and with the point of trying to create and edit interactive virtual worlds just by prompting them. Cool. So here is a case study. I have some kind of virtual scene in the Unity engine, and I would like to expose large models at runtime inside of this thing to allow any gamer to just change games on the fly. And I'll give you a very short kind of example of how an interaction with the system could work and how that informs building such a multi-agent framework, at least a very simple version of it. So typically, you need a problem statement and what you want to achieve out of this. The problem statement for me is I want to be able to edit existing game scenes arbitrarily given the user request. I'll take a very simple example here and work through how we would build such a system. So I have this toy room, and the simplest user prompt that I could come up with is, hey, let's make this bear twice as big. Now, what does it take to actually make this happen? So realistically speaking, I have this user request, and then I have this virtual scene. Behind the, if you know anything about game engines, this is really complicated. The scene is actually a massive collection of 3D models. They have their names, they have positions, scales, rotations, they have textures, different shaders, and so on. The whole scene is really just this big you can reduce it to a string of text, that's some kind of JSON that contains all of these things in it. This is kind of a messy representation, but maybe you could pass this into ChatGPT and do something with it. But if you want to do a multi-agent framework, the first obvious agent here is something that analyzes the scene and simplifies the situation into something that is easier to deal with. So in this case, the scene analyzer is going to be some kind of agent that takes the scene description and finds the relevant object and its properties and finds the name of it in the scene so that you can refer to it properly. In this case, the bear is the bear. Naming kind of worked out nicely. Then you might have another agent that has some sort of library of skills that might be growing over time that just exposes some useful APIs to this overall system and finds the relevant APIs to call given the user request. In this case, I'm going to skip over this because this is a really simple request. And then this is something that you would then send to some sort of builder/coder, something that is meant to write code, in this case in C#, because that's the engine, that's the language that the engine uses. And it writes a code that is pretty reasonable, pretty simple. But you'll find that this code actually doesn't work. And what we add to this is a sort of a feedback loop with an inspector. And what the inspector is supposed to do is it's looking at the builder's output, and it's seeing whether it's violated any rules that we know about code for this game engine. And in this case, and what this inspector is supposed to do is look at this code, reason about it, and say whether the code will be successful or not, even without trying to compile anything, and seeing whether it violates any sort of rules about this code. If it does, say that it's failed and make suggestions for improvement. This is, we run this kind of thing in a feedback loop. The reason for this is sort of the following. It's easier to verify code than write it in the first place. This is sort of the P versus NP question. And we're hoping here with this kind of design to use this fact that I can kind of look at a code and say that it's probably going to fail. And it's going to be a little bit easier than me actually just sitting down and writing this in the first place. So if you run this kind of iteration once, twice, maybe 3 times, in this case just once, you make suggestions, the builder rewrites the code, the inspector looks at it, decides that, hey, this time this works. You send it to a compiler. If the compiler throws any errors, you send it back again with another feedback loop. And then hopefully the compiler outputs something and it works. And in this case, you get the bear twice as big. But you can do, you could modify this with arbitrary other things, make things like the ball bounce when I click on it, make other objects in the scene interactive, things like this. Now, why did I say that this thing works? I could have done the same thing with ChatGPT, and maybe it would have worked. We need some kind of evaluation, and I need to give you some kind of reasons to believe that this thing makes sense. The way that I can evaluate it is have an existing scene or maybe an empty scene and just have a set of prompts that I'm going to be throwing at the system to edit the scenes or add things to it and see how well it does. And by how well it does, I mean, can it write code that compiles without any errors? That's like the lowest bar possible. And it turns out that if you just throw GPT-4 at this, you give it 0 examples, it will fail about 85+% of the time. If you give it a few more prompts, then it sort of starts working, but it still kind of fails. This overall system that I just told you that had just these few elements, it improves this performance by 3 to 4 times, depending on whether you're creating empty scenes or editing existing scenes. So this is me showing you that this multi-agent framework gives you 4 times X performance. Here's another reason why this might work, and work kind of surprisingly well to have a multi-agent framework. If I do a very complicated task, which is I throw the system at something that is meant to, say, articulate a virtual hand and ask it to do a peace sign, and I'm not giving it any visual feedback. This is purely thrown text. If I ask this system that I just showed to you to grab this hand that can modify its joints positions and rotations, and ask it to give me a peace sign, it's going to do this thing that is on the left, which is really crappy. But if I have another module now that just does this kind of high-level reasoning, giving you a high-level, sort of world model of how a concept works, in this case, how a hand works and its joints and so on, and you just prompt the system to do this, and you use that now as input into this overall system with the kind of constraints that the hand has, you suddenly get something that works. So overall, you can start building this kind of really big complex architectures. And this is sort of showing you how you would start sort of going from a smaller thing and getting to a more and more complex multi-agent architecture that does something interesting. And this is my time to hand it off to Amber, but I will take any questions while Amber switches over.
Cool. Thanks, Andy. Yeah, I see that's perfect segue to go with Amber and showing how to get started using Autogen for the competition. I don't think we have any questions.
But I can hope that, through Andy's talk, we can inspire folks to think about how you would approach these questions with multi-agent. And you will see in part of Amber's talk, she actually takes a lot of components from these things that Andy has described.
Thanks, Andre. Okay, so just making sure that you see my slides. Everything looks good. Okay, great. My name is Amber, and we just heard Andre's presentation of all the awesome reasons why what Autogen can do. So I'm here to talk to you about how you can get started and kind of our thought process around building the Hacker Cup AI starter kit. So first, I just wanted to touch on some of the stuff that Thomas had talked about yesterday, and that's just the experimental design setup. So we have this input, which is our markdown problem file. We have a couple of sample input outputs. We do have an input and output, which are like the full inputs and outputs, somewhere around like 600 examples. And you will not get this for the competition, but it could be really helpful for just evaluating while you're experimenting, and any associated images with those problem files. So it's our job to kind of figure out what kind of systems do we want to build. We just heard all the great points about using these agents in a feedback loop. So maybe we can do that to kind of produce our output, which is hopefully some working code. So in order to get started, we decided to use this dim sum delivery problem, which is part of the 2023 practice round problems. And we did that for two reasons. One, I mean, who doesn't love dumplings? But two, because it kind of involves some kind of trick. And so it's actually not a very code heavy problem. It's kind of more logical. So we thought this might be a good test case for using an agent framework. When we tested it with GPT-4o with just one shot, it failed. So we wanted to see what it could do with inside this agent framework. So I'm going to give you a little bit of background on what this problem is about, and then I'll show you kind of some of the approaches that we did in order to do the starter kit. So this problem starts with this restaurant called Dim Sum, where we have two characters, Alice and Bob. They work at this restaurant pushing a cart of dumplings to a certain customer. And so you can imagine that the dining room kind of looks like this, where we have a bunch of tables that are in columns and rows. So we can kind of think of it as a grid. So we have our two characters here, Alice and Bob, and they have the dumpling mobile. And their idea is we need to push this dumpling to specified row column of said customer. So that's in red. So to make it more fun and interesting, they've developed some game. So the idea behind the game is that there's stipulations on how each one can move within the grid. So for example, we have a sample input, which would be here. So right here we have our rows and columns, so that's our grid size. But Alice, she can only move down rows. So she can only move between 1 and A, in this particular case, 1 and 2 rows down. But Bob, he can move between 1 and B rows to the right. And so the goal is to be the person that pushes the dumplings to the row and column, so the location of the customer. And so that person wins, and our goal is to figure out what conditions guarantee Alice to win. And so a couple other things. So if Alice reaches the row of the desired customer, but she's not at the customer, then she loses her turn. And likewise, Bob, if he reaches the column of the customer, but isn't at that customer, he loses his turn. So maybe that's all super confusing. So I'm just going to go through an example right now, and hopefully that will clear this up. And if not, you can look at the actual problem that David posted in the chat. So I'm going to go through, first would be Alice's turn, and Alice always starts. So remember, she can move between 1 and 2 moves. And so in this particular case, she can move either here or here. And so then let's say she moved here, and then now it's Bob's turn. So Bob can move between 1 and 1 moves. And so Bob will move here. And so now it would be Alice's turn, but because we're at that row where our desired table is at already, she doesn't have any moves left, so it's Bob's turn again. So now Bob, brings the dumplings to the table and gets all the glory. So then you're thinking like, oh, okay, well, technically Alice did have another pathway, so maybe she could have won that way. So we can kind of explore that other path, the other route she could have gone. So she could have gone to this square, and then Bob would move and do his turn, and now it's Alice's turn again. And in this particular case, it's now Bob's turn, and he is going to also win. So if you run this through a couple of times, what you'll see is that the grid size is kind of depictive of who will actually win. So it's in both of their best interest to kind of go as slowly through the grid so they don't run out of space. So you can think about it as like if she was to just go all the way down in this particular grid, she would have got stuck sooner. So if we were to change the grid to being something like this is actually advantageous for Bob because now he has more room to work with. So essentially she just gets stuck and he's able to, go in for all the glory, and he'll win in this grid size. But in a different size where Alice has the advantage, then when they both play optimally, Alice should win. So this actually ends up being a pretty simplistic answer where it's just this conditional statement. So we were like, okay, let's see what we can do when we put it into an agent framework. So we first started with this really simple approach with just using these 4 agents. And I'm going to kind of illustrate how these 4 agents work together. So we first have this vision agent, and this is really important because remember I told you we have those images, and so now we need to figure out how are we going to use those images. So what we do is we send in those initial prompts with these image tags, and then we're hoping to get back some a caption prompt. And to facilitate all of these conversations with the different agents, we have what we're calling as a project manager. It's just an agent that is able to relay and communicate between all of the different agents that we're going to be working with. And let's see how that's set up in Python. So for the project manager, we set that up using the user proxy agent in Autogen, which is just a built-in class. There's different parameters that you could put onto this user proxy agent. You can use it with or without human input. Obviously for this competition, we're using it without, but the most important thing is I wanted to show you the system message, and we kind of template our system message in a certain way, which you can use, or you can define your own method to do it. But this is how we ended up doing it, where we define the role of that agent and then we kind of just tell it like how we want it to interact with the different agents. So in this particular case, how we want it to start, how we want it to manage the other agents, and then how we want it to end the conversation. Like what are the end conditions that we want for this agent? And then for the vision agent, there's a couple of different syntaxes that you can use for images within Autogen. So it really wants to have this image tag in either a file path or a base64 string. And then we specify like what we want it to do with that. In this particular case, replace that image tag with a caption in the prompt. And so in Python, that looks like this. We have this assistant agent class in Autogen. And similarly, we just create a system message that just tells it like what it is and what we want it to do. But the most important part is you need to attach this vision capability. And this is a class in Autogen that gives it that ability to read those image tags. So now we have our caption prompt. So now we're going to make that feedback loop like Andre was talking about earlier, and between our coder and our evaluator. So this is going to just go through, create a solution, and then see if it's passing or failing our sample cases. And how we're going to do that is we're going to create what's called a group chat. And so in Autogen, they have this group chat class, and we just specify what agents are involved. This is a pretty simple one where we only have these 3. You can add in things like history, how many rounds you want to go, the style that you want to communicate, like the order. And I think the default is just going in the order that we specify in the agents list. And then we have this group chat manager class, which is what we attach the group chat to, and that's what we interact with. And so pretty simple. And so when we did this, what we found was ultimately it failed. It really loved this like modular arithmetic answer. So we realized what we need to do is we need to break it out of this, pigeonhole response and try to get it to be more creative. And we did that by creating 2 new agents. We have a problem analyst and a solution architect. And the idea between this is that we would use these agents first to basically give us all the information that we can about the problem. So like all the constraints, all the assumptions, make sure that the goal is super clear so that we can pass that to our solution architect. Our solution architect is going to create like 2 to 4 plans for us that are unique that we can execute on so that we can go back to our whole feedback loop and be able to evaluate if any of those are worth doing. So what we'll do is we'll go and we'll code one and see if that passes or fails. And then if it fails, then we'll try it again. And then if that fails again, we'll just switch over to plan B. And so then we'll see if that one passes or fails. And if that one passes, then great, we're done. If it fails, then we can go back to that solution architect and be like, hey, all these plans failed, write me some new plans. So when we had tried to do it with this design, which is currently what is in the Hacker Cup starter kit, it worked for some of the easier problems like the cheeseburger problem, but for the dim sum problem, like we were able to break out of the modular arithmetic and get more unique solutions, but we were not able to get the solution that we were looking for. So that'll be a really interesting experiment for you. I'm very curious if you end up getting that to work. And so some of our learnings, though, from this experience was that these agents really love to code. You might have seen it in our vision agent. We put in there like negatives of like, you cannot code. Even if you don't give it that ability, sometimes they like to do pseudocode. So that can be a really interesting thing to work with. And then they don't really like to logic, as we've seen with this problem. Another thing is like we do have that large input that we are using for evaluation, and that can be really challenging. David posted in the chat a gist, which was kind of a function that we created to use this, but it was just very simple. And like the idea was like we were going to be able to use that to evaluate if our code was working. But what we found was sometimes it would kind of get stuck in a cycle or a loop, and then it wouldn't break out. So it might be a good reference point. We didn't put a lot of effort into making that a little bit more robust. Some other learnings was there are really long development cycles. I would recommend that you start with just one problem and try to get that to understand the interactions and how things are going within your system. And then being very explicit about what agents can do, like their input, how they're interacting, and the output will provide better performance. So if you want to get started today on using this, you can go to this GitHub site. We have everything there for you to get going. And we 100% recommend you use this on Docker. This is Gen AI running who knows what code. So using Docker is your safest bet. And we have all of that ready for you to get going on our README. So you can just go through those steps. We did, for this experiment, use GPT-4o for both the vision and our model, but you can use whatever model that you want. And I think that's everything. Thank you. Do you have any questions?
I do have, but let's see if people have. Let me check YouTube.
Yeah, I think we have a few questions in the YouTube stream. I think, Andy, maybe this one is for you. Is there a specific resource to learn about multi-agent framework you'd recommend? And then I think the second part is, do you know if there's any current, if are they currently applied like in by any companies in real world problems?
So two separate questions. I'll answer the first one. There's many papers. I mean, like the whole field is pretty new, but there are some overview, survey papers on multi-agent kind of, approaches. Maybe the one, there is an April, I think, paper. I can try to drop it into chat later. It's a paper from Guo. It's called Large Language Model-Based Multi-Agents, a survey of progress and challenges. That is still like a few months old. This thing is moving fast. Maybe there is going to be a new overview, in next month or so that might be more relevant. But overall, that is a pretty decent overview. So let me try to drop it somewhere. And for those of you who know how to actually, I'll do that. And to answer the second question, that's difficult to know, partially because, production AI is very much proprietary. I have spoken to people who work with some production systems, and I cannot verify any specific ones. But I can tell you that I have chatted with people who try to design systems like this. And hypothetically, let's say that you were trying to create a chatbot that was exposed at the large production scale, that had access to proprietary data for the company. Maybe it also has, capabilities of searching the internet, is doing some sort of production-like level things like this. And one of the questions that you might have is, hey, do I always want to use the most expensive model, or sometimes maybe I want to use a cheaper model? At that point already, you kind of run into this kind of multi-agent thing in which you're going to figure out how to route this information. Maybe sometimes I can just route to cached, answers, like some FAQ kind of things. If you verify that this is close to FAQ, you can route to that. This is a multi-agent framework that I just described that probably most companies are actually using because it saves you money. So at least at that level, yes. I cannot comment on any specific things that happen within any big companies.
Thanks, Andy. I think, Thomas, you have some questions, right?
No, I was just like, I find that this is really interesting topic, and I really like your presentation, Amber. And yeah, I ran on a single shot, as you saw yesterday, and like I feel that this is the next step. Like basically, you want to have that loop that enables you to to run pieces of code test. And yeah, I'm gonna dig into this. I haven't tried Autogen, so I will give it a try and maybe ping you back. Um, and I was curious if this is like more a development platform, or you can actually put this into production, or when you are ready, like you should like kind of strip out your Autogen and just route your own agents. How do you? Yeah, Autogen, does it scale to put like a server and put it into production? Yes, no.
Amber, do you want to take this question?
Well, I think this would be a great question for the Autogen team. I am not sure.
Okay.
Sorry.
Yeah. No, it probably does, but like, yeah, I'm curious.
So my rough answer is this. There is another approach from Microsoft that was semantic kernel. I know that one scaled, and I know that Autogen is another approach that seems to be competitive. I highly believe that this will scale, but I would like to be proved wrong.
Yeah, but for instance, for this competition, you need to solve all the problems at the same time.
That's easy.
Okay, yeah.
I think when you're asking production, I'm imagining millions of customers joining at the same time. And
no, that's not. Okay.
Yeah, this is a relatively small scale competition, even if we're thinking of it as complicated.
Yeah.
Autogen would be completely, capable of taking.
I think a lot of times also the limitation is in your back end. How many concurrent results can you serve for one single model, and what kind of infrastructure you're using to host these multiple models? So that probably will be the limitation instead of this agent framework.
Yep. Yeah, you're right. And I'm also curious about something that Mark mentioned yesterday about the importance of images for people, but not to describe the problem. Did you try like using the images or not using the images, and if that helped or not? Of course, you're using GPT-4 Omni or something like that support images. Does it help? Like,
Amber, do you want to take this? I mean, I know the answer in some other setting.
I would say from our perspective, I felt like the images were better for our problem analysts when we were using the architecture to kind of define what the problem was doing. So it didn't hurt. Like I said, we didn't get to the right answer. So maybe someone else will be able to, answer that question. But I found that it was helpful.
And I think also depends on the problem itself. So like there are some problem that's very much graph based, and you need to be able to see the graph. Otherwise, just describing the connectivities becomes really wordy. And I think, Andy, you actually have a paper in Europe last year. No, it's not you, but someone has a paper in Europe last year that talks about how these models are quite bad at navigating graph structures.
Yes, I believe this was Ida.
Yeah.
From Microsoft Research. It depends on the graph structure, and again, this was navigating graphs without vision. So the question is, can you feed visual information in a useful way? I have some preliminary results that show that it's decent if you have feedback loops where you can actually act in the visual space as well. So you would want something that can actually modify the original input, and that really gets you somewhere, because then you can kind of sketch on top of this original input and do some kind of reasoning over that. How you implement this becomes really complicated.
Okay. I don't think we have more questions coming from YouTube, nor Discord either. So I think we're gonna wrap it up. And thank you. It was really fun, and actually, I'm gonna try it. I feel a lot of people will get motivated to try agents with a framework that is simple and elegant. So yeah, this is a challenging task, and the problem you picked is tricky. Like the solution is not. I actually tried the same problem, and yeah, I always had like huge graph walking whatever, and yeah, the solution is way simpler than that. So thank you very much for joining, and see you soon.
Well, thanks everyone. Bye.
Bye-bye.
Bye-bye.
Thank you.